Hello, hello. In the fourth and final installment of this project, we look at question number 4. A projectile is launched horizontally from the top of a cliff. So, obviously, we should get our visuals ready, as we have in the past three. So, we have a cliff and a ball. Oh, I just made it a little ball because it makes it fun. So, we have a little ball being launched off a cliff with the velocity going straight out horizontally. So here are just some notes I made by looking at the picture and using outside information. Horizontal velocity is going to be constant the whole way because there's no net force acting upon it. You know, an object in motion stays in motion unless a net force is acting upon it, as we learned through Newton's first law. So now looking at each thing, we see that the vertical acceleration is also going to equal g because, again, other than gravity, there is nothing else acting upon the object. We're not looking at air resistance. So the gravity equals 10 meters per second squared. So we know in the vertical direction, the acceleration is going to be 10 meters per second squared. And in the horizontal direction, there is going to be zero acceleration. So looking at 4A, which asks us to sketch position time, velocity time, and acceleration time graphs. We can look at position time first. So because there is a constant velocity, as we discovered with the initial illustration, there's going to be a constant slope in the position time graph. Now looking at velocity time, you can see that because there's a constant velocity, that's going to be represented by a straight line at whatever numerical value that velocity ends up being. And over time, it's going to stay the exact same. Um, and for acceleration, because constant velocity means zero acceleration, so it's just right along the x-axis, the velocity stays at exactly zero. Okay, moving on to B. We see vertical position time, velocity time, and acceleration graph. So the position time graph is probably the hardest of all of these. Although there's a very, very simple trick to this. It's look at the illustration from before. So if you look at the illustration from before, you can see that as it goes down and the ball accelerates, the velocity is getting more negative and more negative, and over each period of time, the ball is getting way closer to the ground over each instant. So each second, the ball is getting drastically closer to the ground. That means because the vertical velocity is getting more negative, the slope is also getting more and more negative. So we see that it starts at zero and it goes all the way down to almost a vertical line at the axis. So now looking at the velocity graph, this obviously, so it starts out at a zero velocity and keeps getting more and more and more negative. Because there's a constant acceleration, we see that there is a constant slope in this velocity versus time graph. Now for acceleration, again, vertical acceleration is g, so negative 10 meters per second squared. So it's constantly over time, no matter what happens, until it hits the ground, it is at negative 10 meters per second squared. Even when the velocity is zero, this is a trick that's hard for students to understand, but even when the velocity is at zero, at the very instant the ball is launched off the ground, when the vertical velocity is zero, it is still moving at negative 10 meters per second squared. Sorry, its acceleration is still negative 10 meters per second squared. It's not moving at that speed. So, for C, if the projectile's initial speed is 10 meters per second and the cliff's height is 20 meters, how far from the base of the cliff does the projectile land? Now, this is different than 2 for, oh, sorry, different than 3, which had our last uh, uh, kinetic equation, because we need both the x and the y direction. Another thing that students mess up a lot of times is they'll just say, okay, so I found that the acceleration is 10 meters per second squared and the velocity is 10 meters. So just put it in a problem and solve. No, you cannot do that. You have to separate the x and the y, otherwise the problem will make absolutely no sense and everything will be jumbled up and you will not get the answer you are looking for. So we separate x variables and y variables. The x acceleration is 0 because, as we saw earlier, the velocity is constant. It stays at 10 meters per second squared. And we're obviously trying to solve for delta x. However, we really don't have enough information on the x side to just solve for delta x using what we have in delta x. So what we have to look at now is delta y. Delta y, we're given the variables negative 10 meters per second squared for the acceleration. The initial velocity is 0, and delta y is negative 20 meters. Important that it's negative too. A mistake is that, oh, it's 20 meters up, so the delta y is 20. No, the delta y is from the top to the bottom. So that is a difference of negative 20 meters. It is going down 20 meters. So the trick to these type of problems is you have to use t, which doesn't time, which doesn't it's not part of x or y, it's both. Time is a unit that can be used for both, and it is measured in using sorry not using both x and y. So now that we have our y variables, we can solve for t using the equation we find later. And for our x variables, we can use t in our x variables to solve for delta x. So t is great because we can use it for both x and y. It is not in a specific category because t is a constant. Now, looking at our equations, let me switch pages. Again, as we said, solve for t using y variables. So delta y equals v1 times delta t plus 1/2 a times t squared. Again, in this, v1 was 0, so we can just cancel that out. Solve for t algebraically. This is a very crucial step. I haven't explained this in earlier problems, but it's a very crucial step to solve algebraically for the variable you are looking for before you put in and plug in any numbers. Why is this so important? Well, because you have a much less likely chance of making a mistake if you do it algebraically than plug in a bunch of numbers that you may mess up, and you remember the entire time when you have the variable exactly what you're trying to solve for. So you don't have to do multiple things in your head, which a lot of times can mess you up. So we have t equals the square root of delta y over 1/2 times acceleration. So that's t equals the square root of 20 over 5, or t equals the square root of 4, and that simplifies to t equals 2 seconds. So now we solve for delta x using the x variables. Delta x equals v1 times delta t. We can use this problem. Remember last time we couldn't use this problem. We can use this problem because there is a constant velocity in the x direction, as we were talking about earlier. So delta x equals 10 times 2, so 10 meters per second times 2 seconds, meters per second times second. That's gonna leave you with a unit of meters, and you're left with x equals 20 meters. So we've done A, B, and C in 4. We've done 1, 2, 3, and 4. I think that is all the problems we have. Thanks again, Mr. Siegel, for giving me the opportunity to get these problems done. It really wasn't a huge burden. I feel like it was a good way to wrap up the year. I know the um, the catapult project went pretty well for me, but this is another way possibly to boost my grade, and I hope that I ended this, with putting my best foot forward, and that I showed you that I do remember and know a lot of these physics terms. So I will come out of this class remembering a lot. So thanks again for a very successful year, and I look forward to seeing you at graduation. And yes, we made it.